Well, good afternoon, ladies and gentlemen. What is the real difference between ballasted track and ballastless track or fixed track forms? Your answer? No answer? All the beautiful solutions we saw today of ballastless track, they have a flag, a name, a company which is responsible. If you take a ballasted track, no responsibility. The sleepers are made by sleeper producers, the fastenings, a different company, elastic pads somewhere, the ballast comes from somewhere. The next difference is ballastless track was developed by academic ingenuity, so to say, especially from the Munich Technical University in 1970 and the following years. Where does ballast track come from? Somewhere in the dark. Somewhere in the dark. Say 1830, Stockton, Darlington, possibly. And nobody knows. So if we discuss modern track forms, we should also give some thoughts to ballasted track. Because the tradition is so strong that, for instance, you have brand new lines, high-speed lines in Germany made from ballasted track. They perform beautifully for 300 kilometers per hour. You see another section, it's pretty new, it's in Italy. And I tell you that the rails here are colored white, and I leave it with you to consider why. So, but also it's traditional ballasted track. And this ballasted track is a wonder form, isn't it? Taking all the loads, all the speeds, all the strain, being such an old design. So it's high time to give more thoughts to the ballasted track, because there is no advocate for the ballasted track to underline the advantages it has. So consider a track, consider two axle loads, for instance, and we are looking now to the pressure on the bottom of the sleeper. And it's the pressure on the ballast. You see it here. And that means where the maximum is, it is the maximum pressure. And the next is also supporting, less supporting, and again. This is fine and clear. But what I want to point to you is that you have a highly loaded section under the sleeper and a non-loaded section in between. And the situation like this can only be balanced by shear stresses. So our ballast bed is full of shear stresses. Ballast is not very good in taking shear stresses. So what comes out of this? We have high loads here, 12 newtons per square centimeters, yes, and so on. And if we now take a load like this, where we put together two sleepers, then all of a sudden the same consideration brings you to much reduced stresses under the sleeper itself. But this is not the main issue. The main issue is that you have almost every particle in the ballast bed loaded continuously. And the load goes up and down, but you are not jumping from one sleeper to the other. And if you take this, then you can realize that by a longitudinal beam. And this longitudinal beam is here for practical reasons split into pieces. Next thing to say, if we consider the load distribution from this level of ballast underneath the sleeper, how is the load and the pressure distributing into the subgrade? Well, if you look to the most modern books, you find an angle of 45 degrees. If you look to antique books from 1850, you find an angle of 45 degrees. Was it all the same? As a matter of fact, this graph is known, of course, to everybody of you, and it gives a nice distribution of stresses on the subgrade. But we did some measurements, and Mr. Marschnick is amongst us. He did it, actually, and I took the slide out. Stefan, forgive me. Where he is measuring this with an array of load plates. And what did we see? This is the angle I was talking about. This is the pressure under the pressure distribution. And in reality, we found an angle of 17 degrees. And that's a hell of a difference, from 45 to 17 degrees. And if we draw the same picture now, then you see how the load is distributed on the subgrade. And again, it's jumping from one loaded section to the other loaded section, and unloaded, loaded, unloaded, loaded. Again, shear stresses are in the subgrade. And you know the answer of the subgrade, at least if it's rainy and it comes up. So, something is not really understood in our traditional track. And to make a long story short, this is our traditional cross sleeper track as it exists for 180 years, or maybe 170 years. This is what is the combination of a cross sleeper and a longitudinal sleeper, but of course this is practically not to realize, because we should have an infinite long longitudinal beam. So what we did is to cut it into pieces. You see, this is a frame. This is a frame. So we call that the frame track number 1, version number 1. And this, very much to my surprise, is not a brand new idea. Also, in 1854, the famous track engineer, Mr. Carlo Gega, who built the Semmering line, he had on his line this type of track, the combination of a cross sleeper and a longitudinal beam. And I bet that this would have been the standard track of today if they had the timber treatment already invented. At those days, after 3 years, this timber construction was gone, because timber treatment only started from 1863. So, another interesting feature here is how this was embedded. You see it here. No drainage at all. So drainage and the importance of drainage is shown here very nicely, because it doesn't exist here. And I would like to call to everybody who deals with tracks 3 important things you have to observe. Drainage, drainage, drainage. Yeah, and I am very much aware, and it's why I say it here, because I was ever so impressed on the high water tables you suffer from here in England or on the island. And I remember an approach to Heathrow one day, many years back, in the evening sun. And it was glittering from all sides, water all over the place. And then I saw tracks where the water was almost at the crown of the rail. So, take it seriously. seriously, the conditions you have here are difficult, and you are aware as soon as you build a tunnel or if you drill under London. So, this is our first test section, which was laid in 1999. It is 17 years in service now, and it performs beautifully. The other day, just before the InnoTrans, I was there with Korean colleagues, and it is absolutely level. However, we learn our lessons with this type of sleepers because there was also an experimental reinforcement which did not perform so well. But the geometry of the track is almost perfect. And this is another shot of this section of track, and if you look at this, it is really perfect. And here it is the end of our test section, then the track starts pumping. One issue which is, from my point, not taken seriously by many track engineers is the interface between the ballast and the concrete sleeper. If you have a hard concrete sleeper on a hard ballast, you have a very reduced contact area. Actually, it's not more than 3 to maximum 5% of the total we are calculating. It is like a fakir sitting on his nail bed. This is railways, proven technology. And you see that this elastic footing here is certainly one of the big steps forward. It's now, Rudi, you would know, 20 years old or so. And Austrian Railways, for instance, today, since a couple of years, almost every sleeper is a footed sleeper. And this also brought the price down, because in the first instance, it was really, really expensive. So keep that in mind, because with our continuous development of the frames, we also took advantage of this particular item. And you see here, it's now another type, the blue type. You also have a variation in the stiffness and so on. But it is not really to introduce elasticity into track. It is to create a higher percentage of contact. And as a matter of fact, and one lady made a doctoral thesis on that, and she made hundreds of prints to study the contact. You can guess it is about 35 to 40%, which is really in contact. And what does that mean? You have many paths through the ballast bed where loads are transformed, while these small number of contact points gives you very high loads on very particular routes through the ballast bed. So it is uniformity again. Make it as uniform as possible. So this is another section down in Carinthia where we have a line where we can go 160. Unfortunately, the Austrian Railways is a very alpine railway, and there are not many sections where you can go speeds of this magnitude. Also with this old design, one frame here, one frame here, one frame here, and so on. And of course, it is very important in our case that we also have these lines in the sharp curves. This is a line on Geiger's, or a picture of the track of Geiger's Semmering line. And it is a curve with a radius of 170 meters. This is 100 times this distance. And you see, it's again here And on top of this, this is against any regulations. It is a continuously welded rail in the sharp curves, which was not to be made according to the old rules. And it performs nicely. We have also a block there and surveying and so on. And now, how does the longitudinal level develop? The traditional track, which you saw first of all in Graz-Neusiedl, here you have the number of the years. So this is 2000, 2001, and this is 2015, and you see this is tamping interventions. And very rough, it goes up from a standard deviation of 0.6 millimeter to 1.1, from 0.7 to 1.3, from 0.8 to 1.3, so that the trackmaster decides to have a tamping machine run. If you take now the track, which is the same, on the same track, a section before, then you see the results here, again from 2001, 2016, and you saw how it goes, from 0.7, which was also the figure we saw before, but remember, we have been at 1.3, and here we are at 0.91. So the durability of the geometry is much, much better. Well, in the first instance, when we did the first economic calculations, we thought we will double the tamping interventions. Today we must say we will have another long time until the track is being tamped newly. And so, as we are having about 7 test sections throughout Austria, in no one tamping has been done after laying the track, in no one. Now, this was our full frame here. But as I said, we had some problems with the reinforcement. And then the next was, we experienced that the tampers did not realize that the rhythm changed. So we had some hits on the very first cross sleepers or frames. So we discussed and we came back to the idea to have it with a regular spacing of 60 centimeters or 600 millimeters. But again, it's a frame, as you see here. And this used to be the old one, also in a mode where we have straight reinforcements. Of course, the production was very expensive because you have perpendicular pre-stressing. So I had to accept that it is too expensive and we have to forget it. And so we came up with the next idea, but it's also perpendicularly pre-stressed. And of course, it's of a much sturdy design, because there was the interest of the Americans to use it for 35 tons metric axle load. And so we developed this, and we had it on the main line. Of course, we always make tests only on the main line, you know. This is the main line approaching Vienna, and you see very clearly the frame here. You see there 2 fasteners are connected, and you see, of course, also the elastic pad underneath. And this was done after 6 years in track with a main line with 60,000 tons per day, and you see it's absolutely straight, and where the bumps start, there it's the end of the test section. And then we had to transport the Austrian-made cross sleepers of this type to the US. And there the problem of transportation to economic conditions came up. And under the impression, what can we do? It was decided, also with an eye to the production, to split this track here once more. And you see here it's individual sleepers maintaining the longitudinal beam, which is now made of short distances like the chain of a tank. And this is also how the load goes over it. It's not as a sheep food roller, which would be a traditional track. Here, jumping from one to the other, it is now the chain of a tank. And this is taken now in the States, in Pueblo, Colorado, where also some full frames were brought to. But of course, the majority of the material in the test track is of this type. It's the half frame tie, HFT, named by the Americans like this. We say HDS, high duty sleeper. And out of this construction, we built the track in the heavy axle load loop, where they have a continuously revolving train or a rotating train, an unmanned train. Automatically it runs down and produces nothing else than load. But you see one thing more. You see there are 3 dowels in the fastening. And this is an idea of Rudi Schilder. He is here. You see, we can put 2 clips here, but you can also double the clips. So you have double clipped, double clipped, double clipped, double clipped. You get a sturdy construction, and simply by the stiffness of the structure, even without ballasting, you are very safe against buckling. So what we learned there is, number one, that it performed excellently. But we had 2, so to say, fatalities, because the loop has 300-meter radius curves, and that produces high lateral loads to the outside. And 2 of these fasteners could not stand this, and the concrete broke away. So we used this assembly to fasten twice on the inside of the rail and to fasten 1 clip only on the outside of the rail, which performs again beautifully. And I give you some shots of this test section in the desert. The greatest danger here is not the approaching train, it's the rattlesnake. Yes, that's it. And you can see here the double fastener, also here the double fastener. And I must say that I was surprised myself. I thought we will have about a doubling of the tamping cycle. With this track, they have now accumulated 1.6 billion tons. Billion tons. If you remember, we are talking about the need for tamping is about 60 to 100,000 tons. Now we are at 1.6, so it's 8-10 times more in durability. And the Americans also made some more tests, and they publish reports on that, and they have an annual display of results. And this is now the bending stresses in the sleepers. And you see that the bending stress on the conventional, the bending stress on the conventional have a mean here, and then you have these box diagrams. But the stresses in the frame or half-frame ties, half-frame sleepers, it's much more continuous, as you can clearly see here. What we did not discuss, but all of a sudden we had it in the papers. They measured the ballast deterioration. You know, ballast breaks into pieces under the loads, and etc., etc. And so over the years, you have a destruction, an ongoing destruction of ballast, which has also to do with the unevennesses. I said in the first sentences that we do not have a continuous load, but we have a very important theoretical peak to infinite at the edges, and there you always have destruction of ballast. You can go to any track in the world and you dig in. At the end of the sleeper, you dig in. If you are as deep, you are in the dust. You are in the smashed ballast particles. And it's the same here. You see here, this is a conventional sleeper, and this is about the section. You see the material here. And if you take this and please, you have to think the repeated sleepers. This is the longitudinal beam. You see, it's almost no destruction. This definitely will reflect on the lifetime of ballast. Because today we said it's with ballast we have 45, 50 years, and then you have to exchange the ballast. So if that is the case, you have to think how you can design a sleeper to extend the life of the ballast. No doubt the ballast is the weakest part of the design. And so we have to take everything to protect it. So, and here you see now this indication. This is perfect. It's about 40. That's an experimental quotation or an experimental note given between 40 and 80. 40 is excellent and new ballast, and this is 80 is, well, to dump it. And you see, you can say this sleeper is about here, this sleeper is about here. Of course, it's the same tonnage upon it. And for the first test section in the States, they tried a very sharp curve in the Rocky Mountains at Union Pacific. It is laid here and it performs excellently. They wouldn't have believed that it is possible to improve a track to this standard. And of course, and I have no pictures here, we have also made in Austria, but also in the States, bridge approaches. I think in the morning somebody said, you always have a bridge, a bump and a bump. So we inserted a certain number, 10 or 12 frames in front of the bridge to overcome this weak point, and this works beautifully. Now, if that is in principle a ballasted track, then you have the, especially if you think to high speed, we have no tests done so far with high speed, I must admit. But you have the flying ballast problem. And one issue is too much of the ballast, and that the ballast is not compacted. So how does it work? You see, the ballast, the worst thing is that you have so much ballast that ballast is on top of the sleeper. And as the train approaches, this sleeper, this ballast particle starts jumping, and then the wind flow takes it away and puts it somewhere, damaging and injuring or whatsoever. All the high-speed train axles are now protected by polyester shields, because also these ballast particles can hit the axles, and they are very sensitive on such injuries. So what can be done? You can lower the ballast surface. You can brush it out 3 to 4 centimeters below sleeper top, which is a practice done in Germany very successfully over many years. And if it's more, then it's even better, because the lateral stability is so high due to the form of this sleeper. You have not only this, also if you have a double clipping, then you have a rotational resistance, a very high rotational resistance, in which contributes to the high stability. Then the next is ballast compaction and the dynamic track stabilization. I am not, of course, informed on all the accidents or incidents with flying ballast, but I never heard really that we had the flying ballast problem where the dynamic track stabilizer was working. So, and the same was confirmed by the Spanish railways, which did very careful investigations on the flying ballast phenomenon. As a matter of fact, they showed us that the flying ballast always, in the first instance, outside of the rails. Those are the origins of the flying particles. So if you not only put your ballast surface down to 3-4 centimeters below sleeper top, you also should get rid of the ballast on top. You can simply put it down with a brush or other machines.
10 minutes.
Now, of course, always was the question, can we have it mechanically produced or maintained? Yes, we can. We can, in principle, with a standard tamping machine, but as you see here, you have a certain width where no tool can enter. So the first solution is to use a switch tamper. In a switch tamper, you can displace the tamping banks and you can penetrate and do the tamping. This is number one. Number two is that as the two tamping banks are moved sideways, then we should have some component to press ballast to the crossing point here. And you see, one of our experiments was a rotated tool, 54 degrees rotated, which is easily done. You need a second groove. And we did it. And now I'm looking forward, and I hope it works. Is it clear? Ah, Gott, dat is een klumpert. No. Yeah, and you see we had, the test setup was here, different types of sleepers. We have the type number 1, type number 2, and so on. We did it in one thing. And you see the result. The result after one tamping run is, this was the position of the sleepers, this was the position of the rails, and you see how nicely tamped the whole thing is. So we can, in fact, also under-tamp this sleeper with a modified design. So this is one more picture of Pueblo. We are now discussing to conclude this test because the experts say we wouldn't learn something. That's the big difference between track and, say, a new motorcycle. A new motorcycle you can test out and it's beautiful. In track you have to wait 20 years until you get it. And these heavy-duty sleepers here are in regular use at Austrian Railways since last year on various sensitive sections here on the Semmering line. And I have a pamphlet here from the production company, and you see this is one of the sections on the Semmering line where you can find old friends, the cross sleepers and the double fasteners here. And I have a set of such pamphlets with me, and I am unable to decide who gets it. So I will give it to Niall, and it's your responsibility. Well, gentlemen, ladies, thank you very much for your attention.